Starting with this video, let's talk about this identity and prove that here. And later on, this will be used later on as we talk about the general form of the Dalmar-Vaughan theorem, which could be used for understanding roots and powers of complex numbers. So we'll have here the first illustration. This might not be the Dalmar-Vaughan theorem in exact form, but this is actually a preliminary phase for the proof of the Dalmar-Vaughan theorem. We are told here that if we have z sub 1, a certain complex number could also be expressed as x sub 1 plus I y sub 1, which could also be written in this form. We know that to be true. You have r sub 1, its modulo. Then you have times cosine theta sub 1 plus I sine theta sub 1. And we also have another complex number. We also have this equivalence here. And we are going to show that the product of z sub 1 and z sub 2, those two complex numbers, given their illustrations, is just equal to the product of their modulo times we have this form here. So let's show the proof of this again, which would be very essential in proving the Dalmar-Vaughan theorem. So here comes the proof here. Okay, we are going to let the given as it is. So we're not going to write here the entire assume or supposing the actual value for or representation for z sub 1 and z sub 2. Let's simply stick to this as our part of our proof. So what we can do here is when we multiply z sub 1 and z sub 2, we are going to multiply these two notations here. So you will have the first one, r sub 1 cosine theta sub 1 plus I sine theta sub 1. Okay, times r sub 2 times cosine theta sub 2 plus I sine theta sub 2. Okay, so we are going to multiply them. Take note that r sub 1 and r sub 2 are both what they call this one, scalar quantities. So you can take them out. You have r sub 1 times r sub 2 times cosine theta sub 1 plus I sine theta sub 1. And we take out r sub 2 on the second, you will just simply have times cosine theta sub 2 plus I sine theta sub 2. So we have here this form already, close to what is our target. What we can do here is to multiply this, and take note we have binomial times binomial. So please use the FOIL method. So we have here r sub 1, r sub 2. For the first terms, you have your cosine theta sub 1 and cosine theta sub 2. Okay, as you multiply the first terms, then multiply the inner terms, plus you can rearrange them. You can start with the theta sub 1. So you have here, of course, you have I sine theta sub 1 cosine theta sub 2. For the outer terms, I'm talking about these two here. So you have another plus I. So you will start with the I. We have I cosine theta sub 1 sine theta sub 2. And finally, for the last one here, you will have actually the form plus I squared. Let me move this here. Okay. So you have I squared times sine theta sub 1 sine theta sub 2. Okay. That's for the FOIL method of the components. Now moving down, you will have here r sub 1, r sub 2, and then you will have here cosine theta sub 1, cosine theta sub 2. Let me rearrange them, combine them, or place this together with this. This will be our second term. But take note that the square of I is negative 1. Again, the square of I is negative 1. Hence, you will have here the form minus sine theta sub 1, then sine theta sub 2. Okay? I'm rearranging them. This would be my second term. And take note again that the square of I is negative 1. That's why we have that. Then for the remaining two terms, I'm talking about this term and that, I could actually factor out I. Okay? So what will happen here is this. We're going to factor I. The second term, or here, this term I mean, is sine theta sub 1 cosine theta sub 2 plus, as I take out I, this I here. So you will have here cosine theta sub 1, sorry, that's sub 1, and then we have sine theta sub 2. Okay, so this is the result when I interchange and rearrange all those terms. So this is actually cosine. Okay, now what is the reason for this? Because when you try to regroup them, just for this product here, when I group cosine theta sub 1, cosine theta sub 2, and minus sine theta sub 1, sorry, this should be 1, theta sub 1, and then you have sine theta sub 2. That's one group. And the other one is, of course, already grouped as I, sine theta sub 1, cosine theta sub 2, plus cosine theta sub 1, sine theta sub 2. So we have two groups. We can now proceed into the sum and difference formulas, specifically for these two here. When you have cosine, let's say theta sub 1 and cosine theta sub 2, minus the sines of both angles, that's actually equivalent to a sum formula. Okay, take note, it's minus, but it's a sum formula for cosine for both angles. Okay, so you're going to add them. And as for this will tell us actually the sum formula for our sine. This is our sine, theta sub 1 plus theta sub 2. For sine, plus means plus. For cosine, minus here means plus, and the other way around. So this is actually equivalent to, further, r sub 1, r sub 2. So you will have here the form cosine theta sub 1 plus theta sub 2 plus I, and all of this, you have sine theta sub 1 plus theta sub 2. Okay? So this is actually what we are trying to show earlier. Going back here, we have shown that if we're going to multiply here the two complex numbers, this is equal to the product of their modulus, or r. So you have this one here. And what happens to the identity here is cosine, the sum of the angles, plus I, sine of the same angles. So you have here cosine, sine of the angles, plus I, sine of the two angles. So we have shown that this identity is true, and we'll be using the same concept as we add multiple, okay, n number of complex numbers. So we're going to use this concept as we prove the general form of the Kolmogorov theorem later on. Thank you very much for watching.